In the mid-1960s, the world was gripped by the intense rivalry of the Cold War. The United States and the Soviet Union were locked in a deadly competition for supremacy, not just on Earth, but now extending into the vast emptiness of space. The launch of Sputnik in 1957 had shocked America, proving that the Soviets could place objects, and potentially weapons, into orbit. The fear was palpable. What if nuclear bombs could rain down from space without warning? In response, the U.S. Air Force quietly explored radical ideas. One of the most bizarre yet technically grounded concepts was a spacecraft shaped like a classic flying saucer. This was not science fiction inspired by movies or UFO sightings. It was a classified study called the Lenticular Reentry Vehicle, or LRV, a manned orbital platform capable of carrying thermonuclear warheads, patrolling the skies above the planet, and delivering devastating strikes if ordered. The story begins in the late 1950s and early 1960s, a time when aerospace engineers were pushing boundaries. Traditional ballistic missiles like the Atlas and Titan were fast, but inflexible. Once launched, they followed a predictable arc. Space offered new possibilities: persistent surveillance, surprise attacks from unexpected directions, and the ultimate high ground. The Air Force, through contractors like North American Aviation, began studying manned orbital deterrent systems. These were not just satellites. They were crewed vehicles that could loiter in orbit for weeks, monitor enemy activities, and respond instantly to commands from the ground. Among several configurations, winged lifting bodies, ballistic capsules, and more exotic shapes, one stood out for its sheer audacity: the lenticular, or saucer-shaped, design. Why a saucer? The shape wasn't chosen randomly or to mimic popular UFO reports from the era. Aerodynamics played a key role. A lenticular body, a symmetric lens, or disc, offered unique advantages during hypersonic reentry. When plunging back into Earth's atmosphere at speeds exceeding Mach 20, the heat from friction is extreme. A blunt, broad surface creates a strong shock wave that pushes hot plasma away from the vehicle, reducing thermal loads on the structure. The wide diameter also provided natural stability, preventing tumbling. Additionally, the shape could generate some lift, allowing a controlled glide rather than a pure ballistic fall. This meant the craft could maneuver to a precise landing site, perhaps a remote dry lake bed in the American Southwest, and potentially be reused, a radical idea in the 1960s when most reentry vehicles were single-use capsules. The lenticular fascination didn't start with the LRV. It built on earlier experiments. One of the most famous was the Avro Canada VZ-9 Avrocar, developed in the late 1950s. This was a genuine flying saucer prototype funded jointly by the U.S. Air Force and Army. Designed by Avro Canada under John Frost, the Avrocar used the Coanda effect. Exhaust from 3 Continental J69 turbojets drove a central turborotor fan, blowing air downward to create a cushion for vertical takeoff and hovering. In theory, it would transition to forward flight by tilting the thrust. The vehicle was 18 feet in diameter, 3.5 feet high, with a crew of 1 or 2. It looked exactly like the classic flying saucer from 1950s sci-fi. Testing began in 1959 at Avro's facility in Malton, Ontario, and later moved to NASA Ames and Edwards Air Force Base. Unfortunately, reality fell short. The Avrocar could hover only a few feet off the ground due to severe instability. Ground effect caused it to pitch and roll uncontrollably. Maximum speed was around 35 miles per hour, and it never achieved proper forward flight. By 1961, after spending millions, the program was canceled. 2 prototypes were built. One is now at the National Museum of the U.S. Air Force, the other at the U.S. Army Transportation Museum. Despite failure, it proved that governments were seriously exploring disc-shaped vehicles for military advantage, especially VTOL capabilities. Even earlier, in the 1940s during World War II, Charles Zimmerman at NACA proposed radical low-aspect ratio wings. This led to the Vought V-173 flying pancake. Built in 1942, it had a near-circular 23-foot wing, 2 80-horsepower Continental engines driving large wooden propellers, and a pusher configuration. Made of wood and fabric for quick construction, it first flew in November 1942. Test pilot Charles Zimmerman and others found it remarkably stable at low speeds, with excellent short takeoff performance. It could fly as slow as 20 miles per hour without stalling and handled carrier deck operations well. Over 190 flights were logged until 1947. It paved the way for the larger XF-5U fighter version, which was canceled post-war. The flying pancake showed that unconventional circular wings could work aerodynamically, influencing later disc concepts. Hypothetically, if built, the LRV would have escalated the arms race catastrophically. A permanent nuclear presence in orbit changes deterrence. Soviets might respond with their own platforms, perhaps accelerating FOBS, which they tested in the late 1960s. FOBS used ICBMs in partial orbits for southern approaches, evading NORAD radars. An American orbital bomber could trigger preemptive strikes or force treaties earlier. Space militarization might have derailed Apollo or led to orbital battles. Fortunately, sanity prevailed. The LRV remains a what-if of Cold War paranoia, a blend of engineering brilliance and doomsday thinking. It influenced later concepts. Space shuttle borrowed glide reentry ideas, though winged. Modern spaceplanes like X-37B echo reusable orbital platforms, minus nukes. The Cold War taught us space's dual nature, exploration versus weaponization. Projects like LRV remind us how close we came to crossing that line. Today, treaties hold, but tensions rise again with anti-satellite tests and co-orbital threats. History warns, innovation without restraint risks catastrophe. The lenticular shape measures approximately 40 feet in diameter and perhaps 10 to 12 feet thick at the center, tapering to edges. The upper dome housed crew quarters and command modules. Lower flat section managed heat shields of ablative materials like those on Mercury capsules, but scaled up. Control during re-entry came from reaction control thrusters initially, then aerodynamic surfaces, foldable flaps along the rim for lift and drag modulation. Hypersonic lift-to-drag ratio was estimated at 0.5 to 1.0, better than pure capsules, but less than wing designs like Dinosaur. For crew members, rotated shifts. Duty station included radar, optical telescopes, radio intercept gear. Weapons officers monitored targeting computers, primitive by today, but sufficient for 1960s accuracy. Off-duty, sleep in zero-G bags, eat dehydrated meals, exercise on bicycle ergometers. Psychological support was rudimentary, perhaps taped messages from home. Radiation exposure from Van Allen belts required shielding layers of polyethylene or water tanks. Nuclear reactor option, a small snap-like fission system producing heat converted to electricity via thermoelectrics. Risks, meltdown on launch failure, fallout on re-entry. Solar alternative, parabolic mirrors focusing sunlight onto boiler tubes, driving turbines or Stirling engines. Chemical rockets, hypergolic propellants like Aerosine 50 and N2O4 for reliability in vacuum. U.S. considered many ideas. Project Orion with nuclear pulse propulsion, but too wild. Dinosaur for manned reconnaissance and bombardment. Soviet FOBS deployed briefly 1968 to 1983, R-36 missiles in fractional orbits. U.S. response, enhanced early warning satellites. Outer Space Treaty of 1967 prohibited WMD in orbit, signed by both superpowers. Post-2000, LRV-fueled conspiracy theories. Some claim 1960s sightings were test flights. Unlikely, launch would be visible worldwide. Still, shape similarity sparked imaginations. In media, referenced in books like The Day After Roswell, though debunked. Modern models. Fantastic Plastics 1/72nd scale kit revives interest. LRV foreshadowed reusable spacecraft. Shuttle used lifting body principles. Today's Dream Chaser echoes glide re-entry. Military. X-37B orbits secretly for months. Surveillance, not nukes. If tensions escalate, orbital weapons could return. Russia's alleged co-orbital nukes in 2020's rumors echo old fears. The entire concept of the Lenticular Reentry Vehicle represents one of the strangest intersections of Cold War strategy, advanced aerospace engineering, and the public's fascination with unidentified flying objects. While it never progressed beyond paper studies and wind tunnel models, Its existence highlights how seriously military planners took the idea of weaponizing space during the height of superpower rivalry. Engineers at North American Aviation and elsewhere saw real potential in the disk shape for solving the brutal physics of atmospheric reentry while maintaining some measure of control and reusability. At the same time, the political climate shifted rapidly toward arms control agreements that made orbital nuclear platforms untenable. The LRV, therefore, stands as a relic of a moment when humanity stood on the brink of taking its most destructive weapons into the final frontier, only to step back at the last second. By the early 1960s, NASA was also considering lenticular shapes for manned spaceflight. Engineer Alan B. Caylett at Langley Research Center proposed a lenticular capsule for Apollo in 1962, arguing for better reentry control and glide capability. Though rejected in favor of the conical Mercury Gemini Apollo design, Caylett joined North American Aviation shortly after. There, he contributed to the LRV study. NA's 1963 report, compiled by R.J. Oberto, detailed the Lenticular Reentry Vehicle as part of a broader manned orbital deterrent program. The LRV was one of 4 reentry configurations studied: ballistic, winged, lifting body, and lenticular. The LRV itself was envisioned as a 40-foot diameter disc, roughly 12 meters, with a domed upper surface and flat or slightly concave underside. The rear was truncated for engine nozzles and control surfaces. Crew capacity was 4 astronauts for missions up to 6 weeks. Life support included oxygen, water recycling, food stores, waste management, and even exercise equipment to combat zero-G effects. The interior was divided: one section for duty with weapon controls, communications, navigation, another for rest with bunks and galley. An airlock connected to the weapons bay, allowing access without depressurizing the whole craft. Compartments could seal independently in emergencies. Power was a major challenge. Early concepts considered a small nuclear reactor for electricity, about 7 kilowatts needed for systems, sensors, and life support. Shielding would protect the crew from radiation, but safety concerns were huge. Later analyses favored solar thermal systems or advanced batteries and fuel cells. Propulsion for orbital maneuvers used chemical rockets, possibly hypergolic, for reliability. Launch would be on a heavy booster like a modified Titan III or even Saturn-class rocket, placing the LRV in a 300 nautical mile orbit. The payload was chilling, up to 4 thermonuclear warheads in an internal bay, possibly with external pods. These could be MERV-like, though MERV tech was still emerging. The vehicle would function as a fail-safe platform, always in orbit, crew ready to deorbit and strike if ground command confirmed an attack or gave orders. In peacetime, it conducted reconnaissance, photographing Soviet installations with high-resolution cameras. If war came, it performed a deorbit burn, oriented belly-first for reentry, released warheads over targets, then glided home using deployable flaps for control. Reentry heating dissipated across the broad surface. At lower speeds, it skidded to a stop on a flat desert runway. Technically fascinating, but fraught with problems. Radiation shielding in a compact craft was difficult. Long-duration life support was unproven. Gemini missions lasted days, not weeks. Precision reentry guidance in 1960s computers was marginal. The dual role, bomber and glider, forced compromises. Politically, the timing was bad. By 1963, Defense Secretary Robert McNamara was slashing exotic projects, favoring cost-effective ICBMs. The 1967 Outer Space Treaty banned nuclear weapons in orbit, killing any deployment hopes. The X-20 Dinosaur spaceplane was already canceled in 1963. The LRV followed quietly. No full prototype flew. Only wind tunnel models and subscale tests likely occurred. Declassification came in 1999 via FOIA requests. Popular Mechanics published America's Nuclear Flying Saucer in November 2000, stunning readers. The article detailed Oberto's report, artist concepts, and speculation. It fueled UFO theories. Could secret LRV tests explain 1950s, 60s sightings? Probably not. Too heavy, too visible on launch. But the shape overlap was uncanny.